Our final presenter today is Christopher White. He's a systems engineering PhD student at the University of Alabama in Huntsville. He has a bachelor's in aerospace engineering from Iowa State University and was previously a research assistant in the decision process lab in the School of Psychology at Georgia Institute of Technology. His research focuses on decision-making under uncertainty measurement error and value-based engineering and cognitive decision processes. Chris will be presenting his research, Reexamining the Logical Foundation of Engineering Decision-Making Under Uncertainty. Chris, we'll turn it over to you.
It is loading now. Yep, we are good. I'll start now. Good afternoon.
Okay, thank you. Yeah, I'm Chris White. I'm a PhD student working with Brian Mesmer, and about some sort of logical consistency topics, as well as sort of base assumptions built into some engineering decision-making processes. And when I say that, I'm primarily working from a decision-based design perspective. So modeling engineering design as a series of decision problems with some sort of value model or function preference representation, representing stakeholder preferences to be used as an objective function for optimization. And it's pretty important for today's purposes to note that pretty much no matter how much work we put into those models, that objective function we end up with is never going to be perfect. And that in and of itself isn't a huge problem, right? What really matters is the standard we set for kind of how perfect we want it to get. What our standard for validity is and how that's evaluated. And often in decision-based design, you'll see some sort of ordinal standard of validity for these value functions. And this here is probably the most explicitly it's ever stated as an objective function is valid if and only if it rank orders all conceivable outcomes in precisely the same order as does the decision maker. But you can find other statements that are similar to this, if not perfectly identical, in a wide number of works. Now, in many situations, this standard works out great. If we're under certainty and we have a one-to-one relationship between our decision alternatives and the outcomes, it's fine. We can rank the outcomes, pick the alternative that's associated with the best outcome, and we've made the best decision. But if uncertainty is involved and we now have a single alternative being associated with some sort of distribution of outcomes, we now need a couple extra steps. And usually, again, in DBD, that uncertainty is resolved by some sort of expected utility method or expected value where either way, we're taking the mean of a distribution and basing our sort of resulting decision off of the mean of those outcome distributions. That is a problem when you combine these two things, because the mean of a distribution isn't dependent on just the rank order, but on the exact interval relationships as well. It matters exactly what those numbers are. Because when you take the mean of a distribution, we're essentially implicitly assuming that the mean is a valid measure, which means we have to assume that the interval relationships on that measurement scale are consistent, which doesn't match with the validity standard that's often being set. Now, these sort of mismatches of assumptions can show up in all sorts of places, but I think it's particularly an issue when we're kind of synthesizing work from other fields and pulling past decision-making work that was maybe done under different contexts and combining some of them in order to solve these engineering problems. But the issue is that it means that figuring out how useful a certain decision-making procedure is for actually selecting a design alternative is really going to depend on what all assumptions we're making and how those assumptions affect the decision process. And if we start really thinking about mapping that decision-based design, sort of simplified decision representation onto a real-world decision problem, we can start coming up with all sorts of assumptions that either can be made or have to be made in order for those two things to map properly. Here at the highest level, kind of the biggest assumption we could make here is that we have a perfect value measure. And while this is something that is not always a stated assumption. Sometimes with certain methods, this might be kind of necessary for certain things to work. But even below that, we have, kind of a level of assumption that we have perfect rank ordering, and that's where a lot of work kind of takes place. And below that, there's all sorts of assumptions, necessary for the processes that produce that rank ordering that we could also be thinking about. But what's really important here is that I think it's really easy sometimes when we start sort of mapping out all of the different assumptions and things implied by specific mathematical processes to assume that this is just kind of an academic problem that researchers can nitpick over, but it doesn't really matter in the real world. Engineers just need something that can get them pretty close and that'll do the job. But if anything, it's maybe the other way around. Because in academic decision problems, we can assume whatever we want about it. We can assume that we have a perfect value measure. We can assume that we have a perfect rank ordering of the outcomes. In the real world, you don't get to assume what all assumptions are valid and what all aren't. So something that's become an increasingly big part of this project is how can we demonstrate the impact of these assumptions and sort of them being held or violated. And as you can probably tell by the title of this slide, one path we've taken is trying to sort of visualize the impact of these assumptions. So if we jump back a little bit to these assumptions, we can now think about a situation where we are explicitly relaxing this assumption of a perfect value measure and operating as though we have a perfect rank ordering of outcomes. And so we can look at, say, two highly simplified, pretty abstract decision alternatives, A and B, where we've got A in blue, which has a slightly higher mean, but also higher variance than alternative B in red. But what's really important to note here is that the shape of these two distributions only looks like this for this specific value representation. And if our only standard is that we have perfect rank ordering of the outcomes, we can't tell the difference between any value scale that produces those same orders. So one way we can kind of think about enforcing this, making sort of more explicit the possibility of alternate interval relationships in our measurement scales, is to actively manipulate the measurement scale to change the intervals. So we're going to be looking at two different ways to do this. This first one is using kind of this sine function to where we basically are taking points every unit along this value scale. And instead of having a one value unit gap between those points, we're going to rescale it so that we have anywhere from a 0.3 to a 1.7 unit gap, according to this function with this manipulation index t, which is more or less just changing where in the sine wave it starts so we can get different related manipulations. Now, this is probably pretty hard to see what's going on, but if we start actually plotting these new measurement scales, I think it starts to become a lot more intuitive. Where here along the horizontal axis, we have the original value scale, and on the vertical axis, we have our new manipulated value scales, where the dashed line through the middle is essentially no change. If we were to have not altered the scales at all, that's what the blue line would look like. But here, places where we have a more horizontal slope are places where we're essentially contracting the value scale. We're pinching it together. There's less difference in value of outcomes in that range than we had previously represented. And places where we have a more vertical slope are places where we have sort of more difference between the value of those points, and it's being stretched out. In terms of what that does to the shape of these distributions, we can come back and we have these plotted on a slightly different scale now. But importantly, we've added these black circles along the bottom, which are essentially tracking the value of specific outcomes as we perform these manipulations. So now looking at this process play out, we can kind of see the wave of contraction and expansion move across here and see not just that one static original value scale, but this whole family of decision alternatives that are all producing the same rank order. And the relevant question here is what happens to the means of these distributions as we look at these alternate measurement scales. And here the vertical lines are representing the means of two distributions. And right there, you can see a little preference reversal, where this is plotting more or less the same results for the mean, but in a slightly different format across that manipulation index. So this is looking at all the different scales we hit along that like periodic motion. And we can see pretty clearly at the ends, we are preferring B. In the middle, we are preferring alternative A. And that really matters because, again, if our only standard is that ordinal consistency, we can't tell the difference between any of these value scales. Now, while that method produces some nice figures and the kind of wiggling probability distribution effect is kind of fun to look at and intuitive, outside of that, it's not necessarily a super useful method. This is a little bit of a party trick. But with a couple changes, I think we can look at a much more thorough way to explore the impact of these interval disruptions, whatever you want to call them. So that brings us to the second method of measurement scale manipulation, where rather than putting that sine wave over those single unit differences, we are dividing that region of interest into 10 regions and essentially in a random order, randomly resizing those regions sort of in one chunk. So there's a lot of different ways you could do it. Here we took the 9 interior points separating those 10 regions and kind of one at a time place them into the appropriate range. So the first point could go anywhere in the range. Second one, depending on if it was lower or higher than the previous point, either goes below or above that point, just uniform random over the appropriate area. And so instead of that nice, clean, orderly manipulation of the measurement scale, we end up with something that potentially is a bit more like this. And even this is kind of a cherry-picked example to be similar to the types of manipulations that we had before. But of course, we're doing this a whole bunch, so we're not dealing with just those somewhat, at least, orderly manipulations, but all of these we're hitting here, which some of these are pretty radical deviations in terms of the interval relationships between any 2 points along this scale. This is also kind of messy enough that looking at the distributions doesn't really do us a whole lot of good, but for just 2 alternatives, we can plot a like histogram of the mean difference between them to look at the decisions that we would be making. So here on the left, we have a histogram of mean of A minus mean of B. So all of these blue boxes are situations where we would have selected A. All of the red boxes are situations where we would have selected B. As we can see, again, we've got a decent number of each. And it's maybe a bit important to point out that we do have a different amount of B. There's a lot more B preferred measurement scales with this method than with the other one, which just shows that the way you go about manipulating those measurement scales can really have an impact on what sort of effects you're going to find. And if you're not careful, you might not find effects that are potentially of a lot of theoretical interest to you at that time. But maybe more importantly, at kind of the small scale of these results is the difference between looking at mean-based decisions versus something like median-based decisions, where this is a similar histogram, but of median of A minus median of B, where we see no preference reversals, which shouldn't come as a big surprise because unlike the mean, the median does actually only rely on the ordinal relationship between all those points. And we can think about median-based decision-making as kind of a special case of, I think, what's sometimes called like quantile maximization in decision-making, which is a technique that shows up in some fields quite a bit, but I don't think you really see in engineering applications as much. But depending on the validity standards we're setting, maybe this is a more relevant method than we have been giving it credit in the past. But the specific results there aren't the only thing we're interested in. It's also really important to ask, like, what is this method doing? And I want to point out that it's not just about trying to estimate the possible measurement error, which is good because it's not necessarily going to be doing a super accurate job of that. But much more importantly, what this does is let us kind of force the relaxation of certain assumptions. It's one thing for us to say that we only care about the ordinal relationships, and we're not really trusting or putting too much stock in the specific values assigned to individual outcomes. It's a very different thing to force us to be unable to trust the specific values by manipulating them. And it's kind of a way to start putting our money where our mouth is, so to speak, with some of these stated assumptions about our decision-making methods. But also another thing that it does, and something that's pretty important for what in my mind is still really early work on this kind of chain of research that we're on here, in starting some really useful conversations about measurement error and giving a jumping off point to highlight some things that could be apparent otherwise, but might not be as readily apparent without these sorts of examples. So a great example of that is the similarities between this and exponential utility functions, which these are both doing kind of a similar thing. And so in a way, it really shouldn't be any sort of shock that these measurement scale manipulations can swap the rank ordering of means, because we do it intentionally all the time to represent an aspect of the problem that we were otherwise missing with utility functions. But depending on how we go about validating models, these sorts of things could be present all the time, and we're not paying attention to it, which is a problem because it changes our answer. And another thing that shows up sometimes is the similarities and differences between this approach, which is changing the specific value assigned to certain outcomes, versus changing the probability of those outcomes while keeping the same value. Because both of these two things could be, changing the probability distributions over those outcomes in a similar way. But when we start thinking about more real-world applications of these decision-making methods, those errors come from different places. And the way that we would try to check and control for those errors are different. And so while there's important similarities between them, we do really need to acknowledge that these are sort of independent avenues that some of this measurement error can get introduced into the process. But also it gives us a sort of a starting point to start talking about what the real world measurement error in an actual value model might look like. Because this was all done, assuming that we had perfect rank ordering. If we start relaxing that assumption, we now have to be really concerned with how that model was constructed and how we got there. And so that has a lot of implications for both, the type of model we're trying to fit and the fitness metrics we're choosing, but also like just the data set we have and where we got that data. And if we can tell those data sets apart, and if we're in a situation where we could conceivably, in kind of a slightly different scenarios, end up with multiple different data sets that we all could be using to fit our value models, what does that have for, or what implication does that have for the reliability of our answers? And the further down in these assumptions we start talking, the more important some of these real low-level base assumptions start to become, like the existence or knowability of a single preference scale that we're trying to map to, which in many situations might be a perfectly safe assumption to make. But there are some situations in engineering decision-making where that assumption maybe starts becoming more relevant than it would be in other situations, particularly when we're dealing with like large-scale, complex engineered systems, where we might have development times in years or even decades for some systems. And so some of these models might be trying to model the preference for outcomes that might not be experienced for years. Is that even possible? Do those preferences exist? Are we trying to represent the preferences for those when the decision is made, or forecast into the future and predict preferences in 10 years? And how close can we get? How do we know how close we are? When we're talking about those timescales, though, it's also really important to think about, what our stakeholders are, what we mean by that. Are the decision maker in question, is it us, a designer? Is it an external stakeholder that has interests in this? Are those two terms distinguishable? And while these topics are, by no means unique issues to engineering decision making, I do think that they are perhaps uniquely relevant in engineering decision making. And these are also things that, if we're not getting kind of strict about the methods we're using and what that implies about the data and how we're manipulating that data, it's really easy for these to kind of go unnoticed. But if we're trying to make decisions that are actually producing the best outcomes in the real world, these become really, really important issues. So this is, a long ways off that we're going to start fully answering these questions, but I think hopefully that gives kind of a perspective on where some of this research is heading. So this work has been funded, at least in part, by the NASA SETDT R&T, and I believe that is it. Thank you.
So can you see the questions?
Yes, yes, I can.
So it starts with Beth Wilson.
Yeah. So how does sensitivity analysis enter into this research? That's something that's come up a couple times. I usually don't frame this as a sensitivity analysis method. It's not the perspective I came to it from, but there's absolutely a whole lot of similarities, and you can absolutely view this as kind of a sensitivity analysis for violations and assumptions, or sensitivity to errors in the actual preference functions that we're producing. So I think that hopefully that kind of addresses it. This can certainly be viewed as kind of a particular type of sensitivity analysis here. So I guess I'll move on and we'll see if there's a follow-up to that. The other question was about chaos engineering. Chaos engineering comes to mind. How do you know what is the best manipulation? Or are you just trying to find one that produces a more informative result? And so that's something that I hoped I kind of was getting at later in the presentation, where there are a lot of different aspects of this problem that you could be examining by trying to look at measurement error here. And in this initial case, we were taking a really, really strict interpretation of that ordinal standard of validity. And so if that is truly your only standard, it is perfectly rank ordering all alternatives, or it's not, then we are kind of in this free roam world where anything that produces the right rank ordering works. I want to be sure to point out here that in the real world, that's not exactly probably the situation where we're in. It's not like we don't know anything about the interval relationships if they're not perfect. We're usually operating in a situation where, the relationships might be pretty good, but not exact. And so there's very important questions for, how far off do these have to be before it starts meaningfully interfering with what we're trying to get done. And that's where I think kind of the later kind of more future work steps of mapping out kind of more specific processes involved in specific decisions, I think would start giving us, more accurate representations to particular problems. I hope that answered your question. I don't know if I kind of talked around it a little bit and went on my own little rant that I was wanting to touch on, but chaos engineering specifically isn't something that we've really looked at here, but it is kind of, it's been mentioned, it's on the books. So especially with it coming up here, it'll be pretty high on my priority list to at least make meaningful connections to, if not, fully implementing or something along those lines. So.
Good. Thank you, Christopher.
Okay, thanks.
Yeah. So last question was a comment. I found this perspective on decision theory very interesting. I did too. Very much so.
Cool. I'm glad.
Okay. Appreciate all of you that presented.